Okay, so I believe we can start now. So smoothly, actually. In the previous class, we briefly learned about the instructions in computer systems. So I explained that the computers cannot understand the high-level languages because it's a computer, it's a machine. So actually, only human can understand the high-level languages. And then, so actually the computers can understand the digital signals. So actually the machine languages. So that means the high-level languages should be translated into the machine languages or machine code. Also, actually, the computer systems are digital systems. So computer systems can only understand the digital signals. And then, the digital signals are composed of only 0 and 1. So it's not easy to recognize some meanings or some words in the machine languages. So, so we use assembly languages. And then assembly language, actually the instructions in our assembly languages are one-to-one mapped to the machine language, so machine code actually. So also these rules or some protocols are defined in instruction set architecture. So actually I posted the instruction set architecture of RISC-V on the Piazza. So you can visit the Piazza resource tab, and then you can find some RISC-V instruction set manual. So instructions in a computer architecture or computer systems are defined in instruction architecture, ISA, instruction set architecture manual. Also, I explained that the instruction set architecture is the interface between software and hardware. So actually we write code with the high-level languages, and then the high-level languages are translated into the machine code and machine languages, and then the hardware receives the instructions in the machine code, and then hardware generates the result defined in instruction set architecture manual. Okay. Okay. So I also explained the concept of the computer system. The computer, this is the, so you need to understand this concept of the computer system. So if instruction is given to the processor, that means the CPU or GPU is the computer processors. And then these instructions are given to the processor, and processor generate the result. So result is defined in the instruction set architecture. And then I explained that what are the results by processors? The results are change of architectural states. So then what are architectural states? So these states are changed by instructions. So there are many kinds of instructions such as arithmetic, data transfer, and control instructions, but only these states are changed in a computer system. So the changed states in a computer systems are defined in instruction set architecture. So what are changed? Data in register files and main memory. So just to remember that. So actually processors are very complex machine, complex digital systems. And then there are many components in the processor. So actually we will learn about the memory hierarchy in the chapter 5. Then you can find that there are many components such as cache memories or TLB and some other architectural components. But you need to remember that only data in register files and main memories can be changed by instructions. So actually, there are many memory components in the computer processor. So cache is the memory components. So data in these components can be changed also if the instruction is executed in the processor. But ISA, the instruction set architecture, just handles the data in register files and main memory. So some intermediate states can be changed, but those are the final result by instructions. So, and then in the previous class, I briefly explained about the RISC-V instructions, and the RISC-V is the RISC type instructions. So that means that the RISC type instruction means, which means the instructions are rather, it's a simpler. So it does not mean the instruction set architecture is simple, but it's simpler than RISC type instructions. Also, RISC-V instruction set architecture is an open source ISAR. So anyone can use these instructions without any royalty. So many industry and academia community have interest in the RISC-V instruction set architecture. So usually the big companies such as Samsung or NVIDIA try to acquire ARM, but they failed. So some processor manufacturers such as Samsung, Qualcomm, and then some other companies, they make ARM-based processor, but they need to pay some royalty to ARM. But if they can make some processors with RISC-V ISAR, then they don't need to pay royalty. So it's good. It's economical. So actually in the Piazza resource tab, I posted the RISC-V instruction set architecture manual, and then I also posted some RISC-V instruction set reference card. It's called green card. So if you purchase the textbook, then you can find the green card on the first page. So actually, I also posted the PDF file that is equivalent to the green card of the textbook. So you can see some summarized instruction set of RISC-V. So actually, I got the third shot of the vaccine last Friday. So I think my talking is not as good as the previous class. Okay. So anyway, let's start today's class. So the first, I will cover the arithmetic operations in the processor. So what are the arithmetic operations? So actually, we are very familiar with these arithmetic operations because calculator. So if you use the calculator, then you can find this type of operations like add, subtract, multiply, or divide. So also the computer processor support the instructions that performs these arithmetic operations. So actually, if you see the RISC-V green card, you can find two arithmetic operations such as add and sub instructions. So sub means subtract operations. And then these instructions have the instruction format like this. So add A, B, C. So if you see the green card of the RISC-V ISA, then you can find that you can find some formats here. Also, you can find that this is the instruction of the RISC-V ISA. Then also you can find the some format of the instructions like this. So here in this slide, the format of the add instruction is add A, B, C. So actually, we will learn about the register file later. So just see the format of the instruction like this: add A, B, C. So if the instruction is given, then definition of an instructions are also explained in the instruction set architecture manual. So what is the definition of a add instruction? So you can find the definition here. The definition is A equal B plus C. So this is the definition of a add instruction. Okay. So how about the sub instruction? It's a subtract instructions. So if you see the RISC-V, the green card, then you can find the sub instruction here. It's a subtract. So what is the format of the sub instruction? Sub. So I believe you can find that. So these are called operands. The format of these arithmetic operands of these arithmetic operand instructions has the same forms. So it's very simple. So if you know the format of the add instruction, so if you see the format of the sub instruction like this. Oops. I'm not familiar with Marco. Sub A, B, C, then what is the definition of this sub instruction? So it's also very simple. A equal B minus C, because it's a subtraction. So what can we find? So add A, B, C. The definition of this instruction is A equal B plus C. So it's A equal B minus C. So add instruction and sub instruction are the same kinds of arithmetic instructions. And then these arithmetic instructions have the same format, very similar format. So why do you use the similar format for the same kind of instructions? Because regularity, it's called the regularity. Then if we use the regular instruction format, then we can make simpler hardware. So simpler processor architecture. And then simpler hardware means that we can make processor with lower manufacturing cost. And then also we can make the faster. So the faster processor. Because if the hardware is simple, then we can use the faster clock. Okay. So that's why the regularity is also important for the performance and then cost of the processor. But you know, in the green card of the RISC-V instructions, we cannot find other arithmetic operations such as multiply or divide. Why? So actually, this is the arithmetic instructions of RISC-V, and then only we can find the add immediate. I also explain about the immediate later, and then subtract, and then we cannot we can understand that these two instructions. So actually, in the arithmetic type instructions, we can find only add and sub instructions. But you know, so we use also multiply or divide instructions in our calculator. So why they are missing? Why are they missing? Okay. Yeah, that's right. Yeah. So one student said that we can also make add, multiply and divide operations with this add or sub instructions. That's right. But another, so if we, but no, that's true. But if we can make some multiply or divide instruction, and then if these instructions are supported by dedicated hardware, then we can make faster faster processor. Okay. So the reason is that actually the multiply and divide instructions are supported by M extensions of RISC-V ISA. So if a processor supports this M extension of RISC-V, then which means the processor supports the multiply and divide instructions. But in this course, we are learning about the RISC-V I here. I extension, so it just to support the add or sub type instructions. But how can you make the multiply or divide instructions? So this is the multiply. More means the multiply instruction, and the div means the divide instruction. Then what is the format of these instructions? The format is the same, like A, B, A, B, C. Then definition is A equal B multiplied by C. How about the divide? A equal, this is C divided by C. So actually, same type of instructions have the same format. So it's called regularity. And then regular format are used, then we can make simple hardware. Okay. So actually, there are several formats of instructions in RISC-V ISA. Actually, I added this slide here. So actually, in this course, we will learn about these 6 types of so we will learn about these 6 formats of the RISC-V instructions, and then actually these arithmetic instructions have R formats here. Okay, so actually we will learn about how to implement the assembly instructions with the machine code or some digital signals. But also you can know that the add has the 3 arguments, so actually 3 operands. And then R-type instructions support these 3 operands here. So that's why the format of the add, sub, and then it's not supported by integer type ISA, but multiply or divide has the same R-type format of the RISC-V ISA. So I also posted the RISC-V instruction set architecture manual, and also you can find some definitions in the manual. So I also copied some definitions here. So these are the integer RISC IB64I integer type instructions. Also, so this is the alphabetical order. So you can find the add instruction here. Also, you can find the description here. So what does that mean? So that means if this instruction actually add RD, RS1, RS2 is given to the processor, then processor performs RS1 plus RS2. So data is also stored in these registers, the source registers, and then the result is stored in the RD. That is the definition. You can find the definition here. So if we know the definition of the instructions, then we can build a processor based on these definitions. Okay, so this is the example. This is the C code that performs F equal G plus H minus I plus J. So you can find that you can find the brackets are here. So how can you translate this C code into the RISC-V assembly code? So it's very simple. We can perform the add operations for G and H. I'm not familiar with this tablet. So we can perform the add operation for G and H and add operation for I and J. So the result of G plus H is stored in the temporary variable. It's called T0. And then also the result of I plus J is stored in the T1. Then we can perform the T0 minus T1. So that's how the C code is working for this statement. And then if this C code is translated into RISC-V assembly code, then this code, this statement is translated into like this. So add T0 GH. So because we've learned how the instructions are defined in RISC-V ISR, we know how this instruction is working in the RISC-V processor. Okay, so if this instruction is executed, then G plus H is performed, and then this is stored in the T0, and I plus J is performed, and then the result is stored in the T1, and then this is the sub instruction. So final result is stored in the F, and then this instruction performs the T0 minus T1. So this example shows how the high-level language is translated into the assembly code. Well, you can find that, the variable name is maintained here, but actually the variable names are not maintained. So we will learn about the operands of the instruction later. Okay, so also I also copied the snippet of the RISC-V green card, so you can find that there are 5 instructions in the arithmetic instructions of RISC-V. Also, you can find some format here. But if you see the green card of the RISC-V ISR, then you can find that, this is the IV32I base, and this is the IV64I or IV128I base. So actually, we are learning about the IV64I. About basic instruction is the IV32I, but we can also focus on the IV64I instruction. Actually, in this course, we are learning about the IV64I. Okay. So just to see this format, also just to see try to understand definition of instructions on the RISC-V green card. Okay, and then okay. Before moving on the next topic of this course, we will take the pop quiz of this course, this class. So, so actually, I will explain about the pop quiz of this course. So pop quiz. Okay. So pop quiz means that it's the somewhat. It's a pop quiz means the. How can I explain? It's a quiz actually, but it's a kind of randomly, and then some. So it's not regular quiz. So it's a pop quiz. So actually, I will show the very simple questions we learned in the previous classes in the pop quiz. So this is the first quiz. So I will show the questions on this slide, and also I will show the quiz via Zoom. And then actually the questions are very simple. I believe if you study hard, you can answer the questions very easily. So actually it's very simple. And then I also generate the quiz in a Blackboard. Okay, so if you access the Blackboard, then you can find the quiz tab, and then quiz number 1 is posted on the Blackboard. So you can then it's actually the answers for these questions are very simple, and then you can submit the answers until the end of today. So that means the 11:59 p.m. of today. Okay, so you can submit the answers via Blackboard. So this is the first quiz, and then I will use. So actually, the answers will be graded by TAs, and then I will use the result of these pop quiz as some attendance check or some understands your some progress in this course. Okay. Actually, I need to find a way to check the attendance more efficiently and then more safely in this course. But actually, the first possible way is to take the pop quiz. So I will give you 3 minutes. So and then just write your answer, and then write your answer on the some blank paper, and then submit the your answers via Blackboard. Okay. Okay, I believe it's enough. Okay, so let's move on to the next topic of the discourse, this class. So actually, as I said, I got the third vaccine shot the last Friday, and then I felt a little bit more tired, and during the weekends, and then I think I'm fine, but now it's not easy. It's not. So actually it's not easy to talk, but I believe it's okay. So we are living in the very hard time. Okay, and then now let's talk about the operands in the computer systems. So, and what are operands? Actually, A equal B plus C. So in this equation, what is this add? Add is called operator, and B and C are operands of this operator, add instruction or add operation. So operands means the data used by an instruction or data used by an operation. So in this equation, B and C are operands of this add operation. Then what are operands of computer instructions? So we learned about the add instruction, add A comma, B comma C. So as you can see, the definition of this add instruction is A equal B plus C, which means these are operands. Okay. So now we will learn about the operands of RISC-V instructions. And then also you need to remember that in the when I reviewed what we learned in the previous class, then I explained that the architectural states are changed by instructions. Then what are architectural states? Register files and memories, main memory. Okay, so which means, so most of instructions are look like this. So instruction name and operands are located after the instruction. So which means, and also I mentioned that register data in register files and main memories are changed by instructions, which means instructions, the computer instructions handle these operands A, B, C, and which means computer instructions handles the data in register file and memory, which means A, B, C can be data in register files and memories. Okay, so we will learn how the operands are assigned to each instruction. Okay, we learned about the arithmetic instructions, so like add A, comma, B, comma, C. And then actually these arithmetic instructions handle data in register files. Okay, so actually file means it's a group. And then register files mean a group of registers. Then what are registers? What is a register? A register is some data array, but the processor can access this data array very quickly. Okay, so register means is the data array which can be quickly accessed by a processor. So we can think that register is the very small memory. Okay, so data can be stored, and then data in this register files are accessed by a processor. It's very similar to memory. Okay, but register is a very fast memory. Okay, what does that mean? So if you write a code, every data is stored in the memory, and then if we just mention a memory in our code, which means a main memory in the computer system. Then what is the main memory of the computer system? It's RAM. So RAM is the main memory of a computer system. So which means every data handled by a program or application is stored in a RAM. But what is the register file? So I also mentioned that register file is the very small memory. Then what does that mean? RAM is the very large memory. So, recently we are using 4 GB or even 6 GB or 8 GB in our smartphone, even smartphone. So which means the memory size is very, very large. But if the memory size is very large, then the speed, which means the performance, the speed of memory becomes very, very slow. And if the memory speed is very slow, then the performance of the computer system is also becomes very slow. So that's the problem. But if the memory size is small, then a processor can access this small memory very quickly. Okay. So processor has very small memory called register, and then processor can access this small memory very quickly. So actually the registers look like this, like R and register index. Okay. And then in the RISC-V processor, RISC-V has 32 register file. So 32 means it's the number of registers. So which means I said the register data structure looks like R and then index. So which means we have registers from R0 to R31. It's 32 registers. So think like this. If we just declare array data like int A32, then we can know that, oh, this array has 32 elements. And then we can access data in this array using the array index. And it's the same to the register file. The register file has the very small number of elements. Actually, RISC-V has the 32 registers. So which means from R0 to R31. And then data is stored one of these register element. And then the arithmetic instructions can access data in this array or the register very quickly. Okay. And then if the array is defined, we also define the size of a single element, right? So if we just declare the array data like this, then also we also define the data type of an array. Then data type is just a size of a single element. Then size in the RISC-V, the size of a single register file is defined by RV blah blah I, this number. Okay, so in the previous class, the base integer i's is called the IV32i, 64i, and 128i. And then this number defines the size of a single register. Okay, and then I mentioned that we are learning about the 64i, so 64-bit computer. So which means the size of a single register is 64-bit. So that's why this processor, this computer is called 64-bit computer or 64-bit processor. Okay. So RISC-V supports 32 registers, and then we are learning about the IV64i, so which means the size of a single register is 64-bit. Then what is the size of this register file? It's 32 multiplied by 64-bit. Okay. How many bits? Sorry. Okay. Actually, but the size of this register file is very, very small. Oh, sorry. So actually 8-bit is the 1 byte, right? I think everyone knows. So actually the size of the one register file is the 8 byte. And then 32 is actually 128 byte. Right? 256. It's a 256 byte. The size of a register file is just the 256 byte. But you know, normally the main memory size is a 4 gigabyte. So compared to the size of the main memory, the size of a register file is extremely small. So which means the register file is extremely fast. Okay. Okay, these register files are called general purpose registers, and then we call each element of this register file, such as the X0 to X31. So actually, I represent the register file like R0 to R31, but in this RISC-V, we represent each register as the X and register number here. So X0 means it's the register number 0. X31 means the register number 31. Okay. And then also you need to know the unit of the some data size, like what is the 8-bit? 8-bit is the byte. And then what is the 32-bit? 32-bit is the 4 byte. And then usually the 4 byte is called word. Okay, it's the 1 word. And then 64-bit. 64-bit is called double word. Okay, it's 8 byte. So I frequently use the this size of the data in this course. So please remember the size of the data, like such as the word, byte, and double word, no, something like that. So we can find another design principle. Smaller is faster. Okay. So why do you use the registers? Because the register file the size of register file is very, very small, which means the process can access register file very quickly. So it's very fast compared to the main memory. The main memory can store large amount of data. So that's good. That's the advantage of the large memory, but the performance is very low. Access speed is very slow. So we use the register file. It's a very small memory to access data very quickly. Smaller is faster. So another design principle. So I explained about the register already. So you can read the definition of registers. I copied this definition from Wikipedia. And then this slide shows the structure of the RISC-V register file. As I explained, RISC-V supports the 32 registers from X0 to X31. Also, this width, the size of a single register file is defined by RV. Some numbers are here. And so we are handling RV64I, so this, which means XLEN, so length of the single register is 64. Okay, and then actually there are 32 registers in the RISC-V ISR. X0 is the special register. So which means X0 only stores all zeros, like 0, 0, 0, 0, 0, 0. Because this is the 64-bit data, there are 64-bit zeros in the X0 here. So actually 0 is stored in the X0. So which means, so add X0, X1, X2. So what is the definition of this instruction? It's X0 equal X1 plus X2. So you know this value can be non-zero value, right? But I said X0 only stores the all zeros on zero value. So even though non-zero value is stored in this X0, the value of the X0 is always 0. So only this is the 0. So what does that mean? This instruction stores some data to X0, but X0 is not changed. So I said that the result of an instruction is to change architectural states, which means the data in register file or memory. And then actually the result of the add instruction, the result of arithmetic instruction is to change the data in register file, right? But this instruction does not change data in X0 because X0 only stores the 0. So actually this instruction does nothing. Even though instruction is executed, the architectural state is not changed. So this instruction does nothing. Okay. So X0 is the special register. So it stores only all zeros. But the data in other registers can be changed by these arithmetic instructions. Okay. Also, even though the RISC-V register files, these registers are called general purpose registers, so which means the registers can be used for any purpose. Okay, but the RISC-V ISR defines the role of each register. Okay. So that's just the recommendation, but problem is that we are using many libraries. So actually, so we combine many libraries, so which means that our application is composed of many procedures such as functions and then some libraries. And then these functions and libraries are following these register purpose. So usually the compiler decides which registers will be used. The compilers translate your high-level language code, and then compilers decide which registers will be used by instructions. So compilers generally follows these some purpose of registers. Okay. So if we see some purpose of registers, x0s are constant value 0, as I explained, and usually x1 is used as the return address. So I will explain about this purpose later. So just see some purpose of registers. Okay. So let's go back to the C code example. It's the same example, but in the previous example, we used this variable name directly, but in a real program, real assembly code, we cannot use this variable name directly. We need to use the registers, okay? Because these add and sub instructions can only access data in register files, okay? So let us assume that f is stored in the x19, and then j is stored in the x23. So you know this is the register number, so which means that it's actually x20. Okay. So how can you write this code? So actually we need g plus h in the temporary register, and then we set the temporary register as the x5. So if you see this previous slides, you can find we can use the x5 to x7, and then x28 to x31 as temporary registers. So we can store the temporary data in these registers. So x20 stores the G, and then x21 stores the H. So we first performs this operation. So temporary x5 stores the G plus H, the result value here, and x6 is the same. And then we perform this final subtract operation. So this is the real assembly code. So just remember that these arithmetic instructions in RISC-V ISA just can access registers, the data in register file. So which means these variables, the data in these variables should be stored in the register files. Okay. So actually this is the high level language code. So I said compiler decides which data is stored in which registers. Okay. So that means compiler decides which registers are used by instructions. So compiler select these registers, and then using these data in these registers, compiler generate the assembly code. Okay. So until now, we learned RISC-V instructions. For example, arithmetic instructions use data in register file. So I frequently use RF or register file as operands. Okay. So the first operand, the first type of operands handled by RISC-V instruction is data in register file. Okay, and then so I also explained that if instruction is executed, the data in main memory can be changed. So which means the instructions also handle data in main memory. So which means the data in main memory can be operands of instruction. Okay. And then I explained that every data handled by applications are stored and accessed in the main memory. So which means if we declare some type of data such as int a, then this data is stored in the main memory. But in the previous, so we learned that this arithmetic instructions handles the data in register file. Then how can you use the data in main memory? Arithmetic instructions can only access the data in register file, but every data, all data is stored in the main memory because main memory is very large. Then how can you access this data? What? Yeah, right. The data in main memory should be transferred to the register file. Okay? It's something like that. This is the large storage, and then this is very small storage, but we can access only this small storage. Then the data in this large storage should be transferred to the small storage. Okay? Then the RISC-V, the computer processor instructions, need to support this data transfer. Okay. So every data is stored in the main memory, but in order to use the data in this main memory, data should be transferred to the register file. RISC-V supports these memory operations. And then two types of memory operations called load and store. So this is the small memory, the register file, and this is the large memory, it's a main memory. So what is load? The load means the data is transferred from main memory to register file. Okay, this is the load instruction. And then store is a direction is inverse. Store instruction means that the data in register file is transferred to the main memory. That is the store instruction. So there are only two types of the data transfer instructions, the load instruction and store instruction. Okay. And then also, then if in order to access the data in the main memory, then we need to know the location of the data. Okay. So in order to access the data in the register file, we need to know the register number. That is the index of register file, right? So we need to specify X0 or X1 or X2. So that is the register number. It's the same to the main memory. So in order to access the data in the main memory, we need to know, so we need to specify the location of data. And then this location of data is called address. Okay? It's the address. This address is very similar to the room number of apartment. Okay? So in order to specify some location of our apartment home, then we need to specify the room number, like a home number. I mean the home number of the our apartment. So it's the same to the data in the main memory. In order to specify the location of the data, we need to specify the address. Okay. So 0x0000, that is the address of the data. So which means if the address is 0, then which means which means our data is stored in the first the first line of the main memory. Okay. And then also when I explain about the size of the architecture of the register file, we also define the size of a single register file. It's also same to the main memory. So if the address is defined, then we need to define the size of the data specified by address 1. Okay. So it means 0x0 address 000 is pointing the some data. Then how about the 0x0001? So we need to define the size of the data specified by address number 1. Okay. So in the computer system, the most of the computer system use the byte address. So which means address number 1 represents the byte, so, which means 8-bit. So address 0 specify the pin number 0 to 7 of the main memory. So this is the 1 byte. Then address number 1 specify the pin number 8 to 15 in the main memory, which is the second byte. So size of this data is the 1 byte. So you need to remember this. Most of the computer system, actually nearly all computer system use the byte address, which means address number 1 represents the 1 byte. So explain this. Also, let's take an example of the high-level language. So this is the snippet of the C code, and then also let's think about the data and address in main memory. So in this code, we declare the variable A, and then we initialize the data in this variable as 0. Also long int, this is the data type. So data type decides the size of data. If this variable A is declared as long int, which means the data size stored in this variable A is 64-bit, which means 8 byte. Okay. So, and then A equal 0, which means the 0 is stored in A, and so 0 is stored in variable A. So I explained that every data, all data handled by a program is stored in the main memory. Okay, so which means if A is declared, then the space for A is assigned in the main memory. So it's a space for variable A. Also, the address. If this space for variable A is assigned in the main memory, then also, which means the address is allocated to this variable A. And then the size of this A is the 8 byte, which means the address from 0x. Some address plus 2 ops. 0x AAA to 0x AAA A plus 7 is assigned to this variable, right? So this, and then 0 is stored in this variable, which means data 0 is the address specified by this variable A is stored in this main memory. Okay, then what is the result of this printf statement? So if we just use just A, then which print is the first statement of printf display the contents of A, right? So the result of this code is 0. This is the C code. And how about the second printf? What is different? We use the AND operation in front of A, which means it's the. So I frequently use this AND operation because I will use the C syntax. So actually, the Python does not support a pointer. Actually, this AND operation represents the pointer, which means actually the address of A. So if we use this AND operator, then this means the address of A. So which means the address of this variable A is displayed by this second printf statement. Okay. How about the array type? So in this equation, so I declare the array type B, and then and then B0 is 0, and then B1 is 1 by this statement here. Okay, so what does that mean? Which means if this array is declared in the C code, then B0 is assigned to some address of the main memory, and then next the B1 is assigned, P2 is assigned, and P3 is assigned like this. And then also, this is the long int. The size of a single element is 8 bytes. So which means if the address of B0 is something like 0x BBB, then what is the address of B1? What is the address of B1? Yes, B plus 8, 0x. BBB plus 8, then B2 is the B plus 16 plus 24. So if the array type is declared, then we can access another element of the array with the offset. What does that mean? The address of B0 is called the base address of array. And then in order to access the B1 or B2 or B3, you can access this data in B1 using the base address plus 8 is the B1. And then plus 16 is the B2. So this value is called the offset. Okay. So in the array type data, the base address is defined for the address of the B0, the first element of an array. And then another element of an array is accessed by base address plus some offset values. Okay. So in this example, the first printf just display the contents of the each element, and then the second line, second printf display the address of each element. Okay. So why do I show it? This array type is widely used, frequently used in our application. And then if this array is compiled, translated by compiler, then we frequently use this offset. Okay. So in this example, the C code is the A12 is 8 plus A8. So which means the data in this address array A8 is stored in the main memory, and then we can access the data in this A8 using this is the offset value, and then this is the base address. Like so, the load instruction or store instruction has this format. The load or store has this is the destination register and offset and source register. And then we usually the source register is the base address of the array, and then this is the destination register. So what does that mean? This load instruction. So this is the address of A8 because this is base address, and then this is the offset for A element A8, and then which means from this address, read data from the main memory, and then store this read data to the destination register X9. Okay, this is the data transfer instruction. And then RISC-V use the little endian address type, so which means that the least significant byte is stored in the smaller number of register. So I will use the if you see this figure, then I believe you can easily understand about the little endian system and the big endian system. So usually, so I said that the most of computers use the byte address, so which means address number 1 represents the 1 byte. But we usually handle the data which have the larger size, like integer has usually the size of integer is 4 bytes. So how can we store the larger size of the data? So if we use the little endian system, the least significant data, least significant bits are stored in the smaller address number, like here. So in this example, this is the 1 byte. So this is the least significant byte. So this least significant byte is stored in the address A, and then the next byte is stored in the A plus 1. This is the little endian system. The big endian is different. So in the big endian system, this data is stored in the smallest address number. This is the big endian system. But usually, many computer systems support the little endian, not big endian. So which means the least significant bytes are stored in the smaller address number. Okay. So this is the little endian and big endian. Okay, so I explained until the memory transfer instruction. Then I think I need to stop here. So any questions? Okay. 한국어로 해도 돼요.
X0에 0을 다 저장해 놓은 그 특수한 레지스터를 쓰는 이유가 뭔가요?
좋은 질문인데요. X0를 아까 말했듯이 어떨 때는 그냥 인스트럭션이 클락만 소비하고 아무것도 안 하는 인스트럭션을 만들어야 될 때도 있어요. 뭐 그거는 이제 좀 더 어드밴스드 레벨을 가면은 배우긴 할 텐데 어떨 때는 그런 인스트럭션이 필요합니다. 그래서 네, 됐나요? 그래서 그런 목적으로 만든 것도 있고, 그다음에 지로 같은 경우에는 굉장히 또 많이 쓰이기 때문에 그러니까는 뭐 지로 같은 경우는 그냥 바로 액세스 할 수 있도록 이제 쓰는 경우도 있고, 예, 뭐 그렇습니다. 네, 그러면은 so I will stop here and then see you in the next class.